Okay, so I will call, and let's see, buddy. So you got 33. I will raise you the rest of your chips there. All right, he's in. How about you?
I'm in too.
You're all in too?
I'm all in.
All right, buddy, what you got? Show me your cards. Let's see, pair of nines. Okay, not bad, I guess. Ooh, 2 pair, kings and threes. That's a really good hand, but Dad's got the full house, aces over queens. Kids are gonna have to go get your piggy banks out again, I'm afraid. Oh, hi there. How are you? We're just playing a little bit of cards here, trying to teach the kids some probability. It's a pretty difficult concept, and they're having a hard time with it. You know, I looked, and last year, the day after the lesson that we just did together, I spent an entire day just taking up questions that students had in class and trying to help them understand what we've learned and how to use combinations and permutations to do counting problems and probability. So let's do that. Let's take a look at everything we've learned and hopefully help you out going forward. So the first thing you'll notice is I've given you a little review table of all the different counting techniques that there are and their associated formulas. And this is all of the formula that we'll do when we're talking about counting methods. First one being factorial, okay, the formula for n factorial. And a factorial basically says how many ways are there to arrange n objects using them all exactly once. So how many ways can 5 students stand in a line? 5 factorial, and so on. We then looked at, well, what if you only want that's a permutation. What if the permutation has a specified length? So maybe you have n objects, but you're only going to have r of them in your permutation or your arrangement. And then we talked about NPR. For example, rearrange the letters in the word aftershock, but only use 6 of those 10 letters. Well, that's a permutation of length 6 from 10 elements. It's 10 factorial divided by 4 factorial, or use the NPR button on your calculator. We then talked about, well, what about the case when you're arranging n different objects, but many of the objects or some of the objects are identical? For example, how many ways can we arrange the letters in the word senseless? Yeah, there's 9 letters, but 4 of them are S's, so we take our 9 factorial and divide by 4 factorial to take into account all the different ways S's can be arranged. And then the 3 factorial is for the 3 E's. We then finally moved on to n choose r, which is the number of ways r objects can be chosen from n total objects, where the order doesn't matter. For example, if I must select 5 students from a class of 25 to complete a special project, how many groups are possible? 25, choose 5. How many ways can you be dealt 5 cards from a deck of cards? 52, choose 5, which is a little over 2.5 million. So in the poker game we were playing, we each had 5 cards. You saw 3 possible poker hands, okay, out of over 2.5 million. Now, one thing really to notice here is that in the first 3, the order matters. You're creating something where there's a specified order. And in the last one, you're doing combinations, the order doesn't matter. Okay, it doesn't matter in poker, the order of my cards. Okay, at the end, I just have 5 cards, and they can be in any order. And I've added this other note, too, that sometimes in probability, we don't have to always use permutations or combinations, and at the end, we'll see a couple examples where that's true. So let's just look at a few examples together. So imagine making a basketball starting lineup for the Toronto Raptors from 12 players. Now, in this example, we're saying a starting lineup not only consists of 5 players, but each player has a position. So if we start thinking about the 5 players, there's kind of an order here, because we're going to assume that, say, for example, Kyle Lowry plays point guard. That's a different lineup than having Kyle Lowry play center. Now, you might argue that it shouldn't be, but we're going to say in this question it is. So this is actually a permutation where the order matters. So we're looking at the number of permutations of length 5 from 12 total objects. In this case, if you use your NPR button, you'll find out there are actually 95,040 possible lineups. That's just a shortcut for saying, look, we have 12 players who could be point guard, times 11 players who could be the shooting guard, times 10 players that could be small forward, times 9 for power forward, and times 8 for center. It's a shortcut, like I said, for doing that calculation. So I'm assigning an order to each player in the starting lineup that corresponds to their position that they're going to play in that game. How many different starting lineups can the coach select if Kyle Lowry has to be the starting point guard and only Marc Gasol or Serge Ibaka can be selected for center? Okay, well, let's assume that the point guard is the first person in our list and the center is second. So I only have one choice. That's got to be Kyle Lowry, but I have two choices for center, either Marc or Serge. Okay, now how about the other three positions? I still have 10 players left for small forward, 9 for power forward, and 8 for whatever position I've missed, shooting guard. That's 1,440. Just those two restrictions really bring your starting lineups down to a much smaller number. This solution assumes, by the way, that if Marc Gasol isn't playing center, he's still available to play one of the other three positions. And if that weren't the case, then we'd have to change those numbers. How many lineups are possible if only 5 of the 12 players are able to play the guard position, point guard or shooting guard? So if we take that very literally, that means we have 5 players for point guard. We only have 4 players for shooting guard because one of them is being the point guard. We've now used 2 players. There are 10 left for, say, the center position, 9 left for, say, the power forward, and 8 left for the small forward or whatever it might be, because that's 14,400. This solution assumes that those 5 players, although they're the only ones that can play point guard or shooting guard, they're still available to play the other positions. The problem didn't say that they weren't available. It's a fair question to ask if you weren't sure. So this example, we're all involving permutations, sometimes using the NPR button in our calculator, sometimes just looking at each spot in the lineup and deciding how many possible choices there were for each, and then multiplying so I get all the possible combinations. Here, order mattered because I said, the position a player plays makes a difference. And that's why it's a permutation and not a combination. Okay, let's try the next one. So here we have a student-teacher hockey team selected from 10 teachers and 30 students, and the team will have 11 players, maybe 2 lineups and a goalie. I don't know. How many possible teams could be created? So we're not going to use positions in this case. We're just going to talk about a hockey team, and it's just a game where they just all go out and play whatever position they want. We have 40 possible people to select from the team for 11 positions. So there's 40, choose 11 possible teams. That is a very large number. Okay, over 2.3 billion possible teams. How about if we add some restrictions? Like, how about there has to be exactly 4 teachers and 7 students on the team? Okay, well, there are 10 teachers. There are 10 choose 4 ways to select those teachers. That's 210. However, there are 30 students, and there are 30 choose 7 ways to pick the the students on the team. That's a much larger number. It's over 2 million. Okay, there it is exactly. And we multiply those together. Okay, because for every combination of teachers, we have to go through every single combination of students, multiply those together to give us the grand total. The number of teams we get now. Is a little bit over 4.2 million. Okay, suppose that Mr. Elliott must be on the team. If the team is chosen at random, so ignoring part B, if the team was just chosen at random, what is the probability that he's on the team? Okay, well, the total number of outcomes is 40, choose 11. Now, how many of those teams have Mr. Elliott on the team? Well, you can look at it this way. If Mr. Elliott has to be on the team, then there are only 39 people for the other 10 positions. 39 choose 10 is the number of teams that Mr. Elliott is on. Now, it works out that way because you're basically saying, like, how many possible teams am I creating out of 39 people where teams are size 10? That's all the possible ones. That's the same as calculating the number of teams that Mr. Elliott is on, because then you're just reducing the problem to basically saying, you have 10 people on a hockey team out of 39. How many are there? Mr. Elliott has to be on the team. You will sometimes see people do this, though. They'll say times one, choose one. There's exactly one way to pick Mr. Elliott on the team. In fact, it's kind of like this example up here with 4 teachers and 7 students. Instead, you're saying one Mr. Elliott and 10 of the other 39 people. If you figure all that out, you get some big numbers, but in the end, you divide it out, you get something that is actually exactly 27.5%. Now, that shouldn't be surprising. We don't actually need to solve the problem that way. Look, there's 40 total people who want to be on the team. What's the probability Mr. Elliott's one of them? 11 out of 40. I have imagine drawing, your name out of a hat and doing it that way. There's 40 people who want to be on the team. There's 11 positions. It's not a big surprise that 11 divided by 40 will still give you 27.5% as well. Imagine there were 20 people on the team instead of 11. Well, you can clearly see that if there's 40 people who want to be on the hockey team and 20 are going to be on the hockey team, that if they're picked at random, you have a 50-50 shot. Well, if there's only 11 people, it's 11 out of 40 as well. So this is without using combinations, pretty easy to figure out what the chances of one person being on the team is. How about if Mr. Elliott and Mr. Darlington refuse to play if the other one is on the team? How many teams are possible with this restriction? So the first thing we might be tempted to do is say, well, let's assume that Mr. Elliott is on the team. And how does that happen? Well, there again, 38 choose 10 teams, or 38 choose 10 times 1 choose 1. And why is that? Because if Mr. Elliott's on the team, there are 10 other positions, and there's 38 other people who can have those 10 positions. Why not 40? Well, because Mr. Elliott's already been chosen for the team, and because Mr. Darlington won't play. But the other possible case, of course, is that Mr. Darlington is on the team. If Mr. Darlington is on the team, it's the exact same calculation. 38 choose 10 times 1 choose 1. Now, I'm just putting 1 choose 1 to kind of explain my thinking. 1 choose 1 is 1. You don't need to do anything like that. Okay, so again, 38 choose 10 because we have 10 remaining positions on the team and 38 players that could take those 10 positions because it can't be Mr. Elliott or Mr. Darlington. Now, first you might think those are the two possibilities, but there's one other big possibility we might miss, and that's that what if neither player is on the team? Because that's okay too. It might be the best solution to the problem. Then there are 38 people that could be on the team. Choose 11 because there are 11 spots on the hockey team. In total, if you do that, you get a number. It's about 2.1 billion. Notice that when we add restrictions, a good way of checking, it's hard to know if your answers are reasonable or not. But one thing we could look at is, look, every answer, as soon as we go to look at part A, anytime we add restrictions, we should expect the number to go down. And sure enough, it does. It goes down a little bit. So for our last example, let's look at a poker hand. So a 5-card poker hand. We should notice that these are all probability questions. So if you're dealt 5 cards from a well-shuffled deck, there's 52 choose 5 possible hands you could have, which is exactly 2,598,960. So what is the probability that all of the cards are face cards? Well, there are 3 face cards, but from 4 different suits, so that's 12 face cards in total. So if we were to look at a probability, our outcome is going to be the 52 choose 5 every single time. Now, how many hands are made entirely of just face cards? Well, there are 12 face cards in the deck. You need all 5 of them. So 12 choose 5 divided by 52 choose 5. Now that works out to 792 over our 2 million and some. It's a very low probability. It's really low, actually. It's about 0.03%. If it helps, this is how I think about this. 52 choose 5 is all the possible poker hands. If I were to write down all the possibilities, that's how many I'd get. 12 choose 5 is the number of ways you can write down 5-card hands that are all face cards. There are 12 choose 5 or 792 ways of writing down all the face cards. One of those would be King, Queen, Jack, all hearts. Another one would be King, Queen of hearts, and then a Jack of diamonds. Another one would be King of hearts, Queen of diamonds, Jack of diamonds, and so on. 792 of them. So basically, it's a way of counting how many cards are there. How many 5-card hands have all face cards, and how many 5-card hands are there in total. We'll come back to that question in just a second, too. How about none of the cards are face cards? That is not the opposite of part A, even though it might seem like it at first. Now I want to count all the hands you could have that consist of cards that are not face cards. Well, if there are 12 cards in the deck that are face cards, there's 52 minus 12, 40 cards that are not face cards. So 40 choose 5 divided by 52 choose 5 will give us our answer. And without showing those big numbers, you get approximately 25.3%. So about a 25.3% chance you'll get 5 cards and not a single one of them will be a face card. Seems kind of reasonable. How about at least one of the cards is a face card? Okay, that is something now where we can use the complement. If none of the cards are face cards, if that doesn't happen, it means that at least one card is a face card. So we really just take 100% and subtract 25.3%. Or we take the number 1 and we subtract that big value there, that value there. So that would be, what's about 74.7% chance that you have at least one face card. Now let's go back up to, let's go with none of the cards are face cards, because I want to show you that there's another way you can do this. Think about doing this example without using combinations. You could treat this as events. Although the order of the cards doesn't matter in the end, we can still think about getting each card in your hand as 5 different events. And if we want no face cards, the probability that the first card we look at being not a face card is 40 out of 52. Times that by the probability the second card is not a face card. Well, that probability now changes a bit because there's only 51 cards left and only 39 of them are non-face cards. And we keep going. That's the probability the third card is also not a face card, times the probability the fourth card is also not a face card, and then times that by the probability the fifth card is not a face card either. If you do that, you will get close to 25.3% as well. In fact, you will. I mean, these are equal. Okay, they are exactly the same. So you don't have to necessarily use combinations. You can think about events as well to answer this problem. And you could also think about events to answer question A as well, that they're all face cards. You could do it that way too. Okay, I hope that clears up some confusion. Please keep those emails coming if you have questions, and good luck. Bye for now.